So friends, last time I talked about the early heroes of electricity and magnetism, like Benjamin Franklin, starting from that time, Gilbert, then Ohm and Ampere and Faraday and Flemings and all those big names which are there overstayed. They collected so much of information about the electricity and magnetism and interrelation between them, that finally Maxwell collected all that information and tried to formulate a theory. Now that finally resulted in what we call the Maxwell's equations, or the theory of electromagnetism as formulated by Maxwell. But interestingly, the whole derivation of those equations in the Maxwell's paper was based on a mechanical model. So he assumes that whatever is the medium, dielectric or whatever, or ether, that has mechanical properties like particles which are there, elastic forces are there, elasticity is there, electrical elasticity and all those kinds of things he takes, he models like that. And then just like a mechanical wave goes through a material by disturbing the particles and then the particles disturbing the next neighbors and so on. So with that kind of model, based on that kind of model, Maxwell formulated all those stories, all those equations, and I admit that when I try to read the two very classic papers in which these equations are derived, I understood very little of it. Okay, and there are so many equations and so, right? But from that it does result that electromagnetic waves should exist. Okay, they should exist if these equations are correct, and if these equations are coming from the observations in the laboratories on currents and magnetic fields and induced EMF, inductance and so on. If these equations describe those experimental observations correctly, and if these descriptions are the main forces which drives all those experiments, then there should also be electromagnetic waves which can travel in some medium or free space and so on. So those things came from Maxwell's equations. But then the Maxwell's equations did not get acceptability because of the background modeling or whatever. And then comes the main character of our story on photoelectric effect, that is this Heinrich Hertz, who was a brilliant physicist, very short-lived, 36 years of age total he lived on this planet. But in that short period, he has really done wonders. And his mathematics and his theoretical understanding and theoretical capabilities were enormous. And he re-derived Maxwell's equations from more fundamental principles, first principles, and gave them the symmetric form that we use today. The Maxwell's equations in the form that we use today are basically given by Hertz and with Heaviside and others. So that was the kind, and then it got acceptability also, right? But then to get that acceptability, not only that he re-derived those things in a much more convincing fashion, but the one for which he is very famous among everyone is that he set his apparatus and designed experiments to test whether this electromagnetic wave can be produced in the laboratory. If the theory says, if the Maxwell's equations say that they should exist, then one should be able to produce them in the laboratory. Oscillating charges will produce such kind of electromagnetic waves. That was the result from Maxwell's equations, and Hertz started working on it. Alright, and what kind of operators he thought, conceived, designed, and then did experiment on that. A very short description, textbook descriptions. Now it's all class 12 stuff. I will slightly elaborate from what I have read from the more elaborate literature, the kind of operators that he has used, the kind of procedure that he has taken to produce those electromagnetic waves in the laboratory. So essentially he takes an LCR circuit. Okay, if you don't know what LCR circuit is, don't worry, the story will still be understandable. So essentially you have LCR circuit is inductor and then capacitor and then resistance and a source. This is the standard LCR circuit that we study in class 12. We do experiments in the labs also. In BSc normally we do experiments on this kind of things. So in the Hertz operators also it was an LCR. So essentially it was some kind of coil, this kind of coil, let us say. But the source here is from a transformer. Okay, so this forms one end, and then you have another end, and this is the transformer, and here you have a normal, say 220 volt and 50 hertz, like that, normal whatever power supply you have. But then this is a step up thing, and it gives here voltage which is quite high, which is, let us say, some kilovolts, 6, 10, 20, 30 kilovolts, so kilovolts, several kilovolts, minimum say 5-6 kilovolts. Okay, and then this is the source, this is that EMF that we are giving to this circuit, and then we have this capacitor here, and then the circuit is not complete. That's the basic part. Circuit is not complete. So there is a gap in the circuit, and here we have very small spheres, separated by a small distance. So the circuit is broken. Okay, but since the high voltage is there, the capacitor is there will be a high voltage across this gap. And if you have high voltage across a gap where air is there, that air can get ionized because of that high voltage across the gap. The high voltage in a small gap means large electric field. And that large electric field can knock out electrons from the air molecules. And then the air may become conducting, because now you have free electrons. If the electric field which is there in this gap and air is there, so that electric field can exert forces on the electrons of those air molecules, and if the forces are strong enough, then those electrons can come out. And if they come out, then you have free electrons which can move and ions, and then this becomes conducting. And it's like as if you have completed the circuit. The moment you complete the circuit, all that LCR thing, the resistance is already there in the circuit, so all that LCR oscillations will start into it. And if LCR starts with this, and if you have L, you have C, then that omega equal to square root 1 by LC, or frequency is omega by 2 pi. So it is like this. With this frequency, you will have oscillations. Okay, and that should produce electromagnetic wave. So that was his kind of idea, and so waves are generated from this circuit, right? Waves are generated from the circuit, but the spark will not be continuous. Once the spark is there, when the conducting path is there, once again that charge accumulation will not be there, because now the charge has a path to flow, and therefore the voltage will decrease and the spark will stop. And once the spark is stopped, once again the same story. Says we are supplying the voltage. Once again this charge will build up here. Once again there will be large potential difference across this. Once again there will be a spark. So intermittently electromagnetic waves are generated from this circuit of frequency, mean frequency at least close to this. Fine. So it is generation. But unless you detect it, unless you see that yes it is there, unless you have some mechanism to receive it and show it, the task is not complete. So there is a receiver, and since it can move, electromagnetic wave means once it is generated, it should move in air or whatever medium is there. And therefore what this Hertz does is put another circuit here, and this circuit was just say a loop, a copper loop, and with some kind of metallic material here, maybe two spheres or one pointed and one sphere with a small gap and so on. And if the wave is generated, and if this wave reaches here, and this wave creates oscillation here, okay, this wave creates EMF here. The wave tries to create currents in this, but once again it is broken. And the same mechanism, if you have some potential difference which is generated here because of this EM wave, then that potential difference may lead to a spark here. So if you have a spark here, that means the wave has reached here. So that's the detection of electromagnetic wave. So you generate it and you detect it. Now in actual experiment, in the real experiment, this gap is adjustable. It is all a very schematic design I am writing here. It's all some kind of screw, micrometer screw, on which these things are fitted, and by rotating that screw, this gap can be adjusted. Okay, so if you reduce the gap, the chances of sparks will be there. And suppose, yes, at this gap, suppose I have a spark. Then increase this gap, right? Increase this gap and see whether you still have a spark here. If you still have a spark here, increase the gap further and see if you have a spark here. So the maximum gap that you can create and still there is a spark. How much maximum gap you can create to get those sparks, to have those sparks. That gives the idea of strength of the wave which is reaching here. If this wave is weak, if the intensity of this wave is low, then at this much of gap there is no spark. But if I reduce and make this much of gap, possibly yes. So this length, spark length, that is related to intensity of the wave received. So physicists design, nobody he did not read it in some book or some journal or some paper. Physicists design their own method and then fabricate apparatus and then do the experiment and get the results. So this was the kind of setup. Now the data, the literature says that these spark lengths were of the order of 1/100 of a millimeter. Remember, 1 millimeter divided by 100. That was the kind of distances. That's the scale. A double of that, 3 times of that, 5 times of that, and so on. But it is of that kind, 1/100 of a millimeter, or a small multiple of that. That was the length. And for how much time? For how much time? Duration of a spark. That was say around microsecond, 10 power minus 6 seconds. So if there is spark for a microsecond and the length of spark is 1/100 millimeter, how difficult it will be to see that there is a spark. Alright, so the whole thing was done, whole experiment was done in some dark room, and eyes are to be adapted to see in that darkness, and then they could observe such kind of sparks and do the experiments. Right? So this kind of experiments he has done to establish that yes, Maxwell's equations predict that there should be electromagnetic waves when you have oscillating fields, electric and magnetic fields. And if you do this kind of, you supply AC and then you oscillate charges in the circuit, they indeed produce electromagnetic wave. Otherwise, with a separation of say 30-40 feet or 10 meters, how can this know that something is going here? So that is known as the Hertz experiment to generate and detect electromagnetic waves, and the formulation of Maxwell's equation by Hertz in a very neat and clean way, convincing way, in a very symmetric way, and then doing the experiment and showing that yes, there are electromagnetic waves one can generate in the lab and detect, that finally establishes that yes, the Maxwell's theory is right. But where is photoelectric effect? Why I am talking all these things in the story of photoelectric effect? That is because to make these sparks visible, when he makes this portion darkened by putting some case or some material around to block the normal light, so that this faint spark can be seen, then he observed something else. Okay, that generation of wave is there, this detection of wave is there, but on top of that he observed something else when he is trying to put those enclosures to make it more dark, and that is where he finds that okay, from the spark, from the light, from this light, okay, there are two things. One is that the spark is there, so light is generated and that light is traveling. Another is because of the spark, the path becomes conducting, and therefore it is an oscillating circuit, and from that oscillating circuit, EM wave is generated. Light is light, frequency 10 power 15 Hertz and so on. Okay, visible light. And this frequency of EM wave, the main EM wave, the target EM wave, is decided by that square root of 1 by inductance into capacitance and so on. So that could be in radio wave region or microwave region. So these are two different things. So the light which is generated from here, that light falls on these spheres or these electrodes or these metal balls, and that is affecting the spark length. this light which falls here is affecting the spark length. And he, by experimentations, he sees that, okay, if my shield is absorbing ultraviolet portion of this light, that causes the spark lengths to decrease. Okay, you know ultraviolet. The visible light has wavelength 400 nanometer to 700 or 750 nanometers of that kind. The portion of this light or radiation which is having wavelengths lower than 400, lower than violet, they are known as ultraviolet. The frequency is higher, wavelength is lower. So that is known as ultraviolet. 300 nanometer, 200 nanometer, 250 nanometers, those will be ultraviolet. So whatever ultraviolet is coming from the spark, if that is stopped, absorbed, then the spark length is reduced. You have to shorten the gap to see the spark. But if ultraviolet is allowed, if that whole light is allowed, especially the UV part is allowed, then the spark length increases. So that was actually the photoelectric effect, and there he sees that this light is also, especially the ultraviolet component of light is also affecting the spark length, and why that is there, and how that is related to photoelectric effect. We will talk of that experiment, but this was the first authentic, documented observations that I have seen, and which is popularly known. There may be many other scientists who might have seen this photoelectric effect kind of thing earlier, but at least I do not know about that. So how he pursued this and how other people pursued that photoelectric effect thing, that will be our next episode of the story.